exercise, we consider how NMR can be used to validate chemical compound in a complex mixture, such as appears in the pharmaceutical preparations. So the whole process can be broken down into the 3 steps. In this step number 1, we identify resonances which are coming exclusively for the compound of interest, and that enables us to quantify the amount of this compound or its concentration in the complex mixture. The next step is concentration determination, and the last step would be analysis of impurities or adjuvants or other compounds which are present in the complex mixtures.
In this section, let me introduce to the main interface of top spin version 4.2.0. So here in the top we have workflow. So typically what we do with the spectra, we process them, then analyze, and then we can do more advanced analysis, which would be then not of our concern today. Here in the top process, we have typical steps in the processing. So Fourier transform, adjust phase, baseline correction, calibrate axis, integration, and so on and so forth. Yeah. So below, this is navigational buttons, which will help us to manipulate the spectrum here in the spectrum pane. For example, we can zoom in, and then we can return back to the full spectrum, or we can shift it up and down, left and right, and so on and so forth. So in the spectrum pane, we have spectrum tab, proc parse tab, which collects all the processing parameters. So for us, only few will be of relevance. Acquisition parameters, which we need to set up to acquire the spectrum at the spectrometer. Title in here. Then pulse program, which is used to collect this, and peaks, integrals, sample description. Here comes the structure of the compound, and these two collect the reporting tabs. So like to make nice output and so on. Yeah, I put into the ULab journal. This is FID, that's the time domain signal which we receive from the spectrometer. So let's revert back to the spectrum. So here we have spectrum exploration tab. So here we have to add our data, and this is the molecule in 2D representation, and here below we have a command line. So here we are going to give a few important comments here below. All right, so let us add data to the spectrum exploration spectrum explorer. So the data I recommend that we put somewhere on the spectrometer, on the desktop, yeah, right here. So data comes as a zip file, so we can unzip and get this directory. So let us revert back to the top spin, and we are going to add our data. So we move to the Spectrum Explorer and then click, right click, and here there is a command called add new data directory. So here we have to specify our directory, and so we go to the desktop, and here is our data folder. So I click OK, and we also can give alias to this, which would be then any name, my data, for example. Okay, so I click here, and my data folder appears here, which contains two types of the work which we're going to do. That's ibuprofen analysis and ubiquitin, which is a small protein. So if we click on the ibuprofen, so here we have two experiments. So one collecting the spectrum of DSS as a chemical shift reference, and so if we click on it and drag in, so we got the spectrum, and the other one is ibuprofen, which we're going to validate. So let's revert back to the DSS as the chemical reference, and here we are starting with the defining its structure. The easiest way to get its structure added here is not actually drawing it. No, it's downloading MOL file from the database. One of the nice sources would be Wikipedia. So we can type DSS NMR. This brings us to the Wikipedia page, and here on the right side we have a reference to PubChem, which is the service from NCBI. So this is the specific link to DSS. So this brings us to the PubChem, and this is DSS, 2D structure, 3D structure. If we scroll down, we can download coordinates. So download please the structures in the format SDF, which is .mol format as well. So when we click it in, so we download the data. Now we can add it to the top spin. So let me revert back to top spin, and here in the structure tab there is this opening interface. Then we will download the DSS structure as SDF, and here there's the structure, so we can actually adjust a little bit its position. Yeah, then we save it, and we can save it to the current experiment number, so that it doesn't really spread all around. So when associated only with the current experiment. So save it. All right, so it's done. Now if we move away and again back to the spectrum, we see that the structure appears here. All right, so the next step is to process this data. As you can see, it's partially processed, but we have to do it, we have to reprocess it. So we go to the process workflow, then select process spectrum, and then here it is. So window multiplication. So we multiply the FID with the window, and here we use exponential window, and then line broadening is 1 hertz. So we can do like 1.2 for a change. So this is our adjusted FID. So now after that we can do Fourier transform. So, and this brings us to the necessity to phase correct the spectrum. So I click on this button, so that would bring the spectrum in the middle of the screen, and so we have to go to the phase, adjust phase. We just click adjust phase, and here there are phase correction buttons. So here is the 0 order phase correction. So now I start changing it, and you can see so it becomes phased. The peak on which I have this red line, which is called pivot point. So I can relocate pivot point to any other place, but then I return back to the most left peak usually. And now I can correct first order phase, and when I correct first order phase, 0 phase will be not changing at the position of the pivot. So now I can adjust the phase of this peak in here. So I can actually zoom a little bit up to see closer to the baseline, and so, and then a little bit more correction. So you can see corrections can be done like in steps. So this is a spectrum, I would say, well corrected. So I can like come back here, and we need to adjust baseline for this. So we move to the next step, baseline correction, and let me show you how to do it manually first. So baseline correction, as you can see, there are linear and then more curved baseline correction. So let me start with linear. So you can see this, my red line can be moved a little bit, and now so my actual baseline is sloping down, so I have to use like higher order to follow this baseline. It usually takes like a few steps to reach satisfactory correction level, like this, for example. Yeah, you can see my baseline is kind of like tracing the noise line pretty tightly. So now I can calculate difference and save it. Okay, so now I return to full spectrum.
analyze spectrum of ibuprofen, we have to calibrate its chemical shift and normalize integrals of its main peaks. For this end, we have to use external reference. So we can use internal reference, but we can also use external reference. So in external reference would be our spectrum of DSS. And here, first step is to understand the spectrum. It contains the lines of the compound itself, DSS, 1, 2, 3, and 4 lines, as well as 2 lines coming from solvents. So singlet line at 3.5 ppm, 3.5 ppm is coming from water in DMSO at singlet line, and another signal at 2.5 ppm right here. So it's coming from the DMSO, which is the pentaplet. As you can see, there are 1, 2, 3, 4, 5 lines in here. So how we can proceed with the referencing? So first of all, we define the position of the most intense line. We can do it either manually by calibrate axis. So we zoom around, then click calibrate axis, and put our cursor on the top and giving 0 ppm. Or alternatively, we can achieve the same by typing the command sref. So once it's done, so we can proceed with the analysis of our ibuprofen spectrum using a Bruker procedure for calibration, which is called heretic 2, which is use of the external reference to calibrate your test spectrum. So in the following, we will do a step-by-step implementation of this heretic 2 procedure.
So the last step in the adding reference is integration. So let me zoom around this area, and then I can go to the Analyze tab, and here there's an Integrate tab. So, and in the Integrate tab, I define the simplest integration process, this one. Then these 2 lines, so define my integral. And this I can also use to calculate concentrations for my test compound. So therefore I have to right click on this integral and then choose heretic and define as heretic reference. So this is standard procedure to define the concentration reference. Yeah? So here this dialog pops up, and then here it says, okay, where the reference spectrum is located is right here. Then what about sample? So concentration of DSS is 10 millimolar per liter. So here is 10 millimolar as it's prepared this way. And then sample volume we can leave blank. And then how many atoms or protons in this case are located within this signal. So we know that they are here. So those methyl groups connected to the silicium. So and then totally 1, 2, 3, 4, 5, 5, 9. Yeah? So I write 9. Okay. And then okay. And finally, overview spectrum. So that's conclude the process of adding chemical shift reference spectrum to the project. Once we set up our chemical shift reference, then we can proceed with the analysis of our test compounds. So I load its spectrum in here and show it's in full. So we can see it needs to be phased. And yeah, let's start from the processing. So we go to the process tab, and then here we define window multiplication. And you can see 0.3, and better to use a bit wider line widths in here, so 1.2, so spectrum becomes less noisy. And the next step would be Fourier transform. So the next would be then Fourier transform in here, and the phase correction. So before I used manual phase correction, so here we can use a shortcut, which is automatic phase correction given by the command APK. So as you can see, pretty decent. So phase is corrected. Now we have to correct baseline. So, and baseline, I prefer to perform like manually. So we move here the line and lift it up a little bit in here. So, and then a little bit down, like here, So we have baseline pretty decently corrected within this region. So now I dealt here, there's a deviation, but there are no peaks here, so I can leave it like this. So this is baseline corrected area, and I save it. So that's my reference spectrum. And again, I click on the spectrum overview. Now we can calibrate chemical shifts using the DSS from the spectrum 1. To perform that calibration, we have to issue the command xiref here. So it reports that EUPAC referencing has been done and all set. So from this point onwards, so we have to start analyzing this spectrum. This can be done in steps again, and the first step would be then to take integrals of all of these peaks and perform the general analysis of the spectrum. Okay, so let me move on to the analysis here, and then there's an integrate. Yes, tab, and we start manual integration of the peaks. So it's pretty straightforward. So we just perform zooming and integration from here to here, from here to here. So now our integrals values are arbitrary. So now we move to integration in this area. This, and finally this. So now we have defined our integrals, and we can save it. And here in the integral tab, we have the list of those integrals. So now we can determine the concentration of our main compound. So we go again to the integrate tab, and then select this integral, and then we say use erratic reference for calibration. We did this, and then calculate concentration. So here it says where's the reference data set. It's right here in the experiment number 1. So, and then region, and then molecule mass, and then so on. So we click OK. And so we provide our concentration. So since here there are 3 atoms, the concentration, correct concentration, which we report would be then this number. So now we zoom around here. So here this is methyl group. So there are 3 protons. So the concentration should be this number divided by 3. So it's roughly 700 millimolar per liter. So that concludes concentration determination. And for the analysis of the spectrum, so we have to export this spectrum and compare it with the predicted spectrum. So to assign all of these lines. So how we can do that? We export this. We save the spectrum as this one DX file. Yeah, and then we put it into the this directory, so we can actually put it to the desktop. So we choose desktop here. Yeah, desktop, and we give the name ibuprofen DX file. Yeah, so then we click OK, and the file is exported. Yeah, of the spectrum. So now we can compare it with the theoretical spectrum. So how we can do that? So we have to open the service, web service, which is called nmrdb.org. So and then here there's a predict 1H NMR. Okay, so we link to it. So, and here we can drop or drag and drop our DX spectrum. Oh, sorry, our molecule, so which would be the ibuprofen molecule. So I have this molecule already downloaded here as ibuprofen SD. So I just load it. All right. So here we are. This is our molecule. And then I click here, simulate spectrum. Since our spectrum measured on the 800 megahertz, so we can actually change this frequency to 800 and simulate spectrum again. This, yeah, here we are. So this is our spectrum, so full spectrum. And now we can compare this spectrum with the actual one, so simulated spectrum. So to do that, we have to paste our DX file right here. Yeah. So it's in the desktop. So ibuprofen DX is this file. So we drop it right here. When we uploaded our gcamp file, which is DX file right here. So we have to click on this tab to superimpose it our experimental file, which now comes in red, with the simulated file, which is spectrum, which is actually in black. So we can zoom around and see, okay, so doublet in the real spectrum, and this is doublet in the predicted spectrum. So now we can even so double click on the screen, so we'll get the full spectrum. And then if we move around, so the molecular structure, you see the assignment is highlighted in here, as well as the peaks, like in here. Okay, this is this yellow is this peak assigned. So let me move it a little bit. Okay, it's jumping here. So yeah, and then you see how this correspondence is defined. So now we can zoom around, and then we can see there's a pretty good fit between the spectra. So we explore peak by peak and figure out so which peaks belong to our test compound. That would be then the validation process if we can account all the peaks here. Yeah, so then we validate its structure. Yeah. So more detailed process of the structure validation is described step by step in the following section. Analysis of impurities starts with the zooming around the area of interest and identification of the solvent signals. So this is DMSO, D6. However, it's very hygroscopic, so it might contain some variable degree of water. So first of all, let's identify DMSO peak. It's this. We can do it by chemical shift. So 253. This peak is DMSO. Let me zoom around it. Here it is. So the residual protonation level is very low because it's deuterated DMSO. So, however, here is the residual water resonance. So this broad hump here at around 3.4 ppm. So is the residual resonance of water in DMSO. So we identified this as the solvent signals, DMSO and water signals. So now let's look at the impurities. So we can zoom up, and this and other resonances, this. So this one and around here are all impurities. We can integrate them and identify the relative concentration. So, but they are pretty small, below fraction of a percent. Let's say this to this peak. So it's yeah, fraction of the percent. It's a pretty clean preparation. So here on that side, we see additional resonances. These are satellite resonances coming from the C13 at natural abundance in the molecule. So it's a natural phenomena. But this one, this resonance is definitely is not coming from our molecule of interest. So that is probably byproduct of the synthesis of this compound. So still this baseline is clean. So we see some compounds, but their concentrations are small. So this concludes our validation. We validated it. So, and we established its concentration. So, which would be then about 794 or 800 millimolar. So, because this is single proton, so we can really take this number as the concentration estimation. So 800 millimolar. And we established that contamination level is below 1%, significantly below 1%. So it's a good preparation. Yeah, that's conclusion.
The most easily accessible NMR observables include chemical shifts of NMR resonances, integrals of NMR resonance peaks, J coupling constants and J coupling splitting patterns. One of the main reasons responsible for the observed variety of NMR spectra is the chemical shift effect, or CSE. CSE refers to the difference in Larmor frequencies of identical nuclei in different chemical environments. The basic phenomenon giving rise to CSE is the presence of microscopic currents induced by an external field B0. The induced currents in atoms and molecules shield nuclei from B0 by creating an additional magnetic field that is proportional to B0. The chemical shifts in the analyzed sample can be referenced relative internal or external standards like DSS, 4,4-dimethyl-4-silapentane, 1-sulfonic acid, in water, or DMSO-D6. For molecules in organic solvents, the external standard is used, for example DSS of predefined concentration in DMSO-D6. To calibrate the reference spectrum, the command SREF is used, which finds a singlet resonance at around 0 ppm and sets it to 0 ppm. This reference spectrum can be used to calibrate the test spectrum using command XIREF, which copies the calibration data from the reference to the test spectrum. The chemical shift effect is important because it fingerprints chemically different populations of nuclei in a sample. That is, the presence of chemically shifted peaks in NMR spectra makes it possible to determine the chemical composition of a sample, as well as to measure the relative amounts of nuclei present in different chemical environments. NMR is unique among common spectroscopic methods in that signal intensities are directly proportional to the number of nuclei causing the signal, provided certain conditions are met. In other words, all absorption coefficients for a given nucleus are identical. This is why proton NMR spectra are routinely integrated, whereas IR and UV spectra are not. In the 1H integrated spectrum of ibuprofen in DMSO-D6, the relative integrals contain information on the number of protons contributing to each peak. It is not possible to directly determine the absolute numbers without additional information, such as a molecular formula. In the example above, the most shielded peak at 0.88 ppm is the strongest peak, most likely stemming from 6 protons in 2-methyl moieties in the isopropyl group. Thus, we can assume that the integral of value 1.0 corresponds to 6 protons. The peak at 1.37 ppm contains 6 times 0.49 equals 3 protons, and thus can be assigned to the methyl protons in the propionate group. The peak at 1.82 contains 6 times 0.167 equals 1 proton and can be assigned either to the propionate group or to the isopropyl group. The peak at 2.4 ppm contains 6 times 0.333 equals 2 protons and assigned to the methylene group. The peak 3.64 ppm contains 6 times 0.2 equals 1.2 protons. The value most likely biased by its location on the slope of a broad hump. After local baseline correction, its integral is amended to 0.167, resulting in the 1 proton contributing to this peak. Thus, this resonance can be assigned either to the single hydrogen in the propionate group or in the isopropyl group. Expansion to the full spectrum reveals 2 more resonances at 7.12 and 7.2 ppm, containing 2 protons each. These peaks can be assigned to the protons in the aromatic group. Thus, using exclusively integrals, all of the non-exchangeable with water protons can be unequivocally assigned, with the exception of the 2 possible assignments of the 2 single hydrogens in the isopropyl and propionate groups. The latter resonances can be unequivocally assigned using J-coupling multiplet patterns. The peak integrals can be used to quantify the concentration of the compounds in the test spectrum relative to the reference spectrum. For example, DSS in DMSO-D6 using Eretic 2 method implemented in topspin. In the first step, the methyl group peak in the reference spectrum is integrated and predefined concentration of DSS is associated with its integral value and the number of protons in the integrated peak. In the case of DSS, 9 methyl protons contribute to the peak. In the second step, the strongest and well-resolved peak in the test spectrum is integrated and the number of protons contributing to this peak is defined. Here, for quantification purposes, the peak assigned to the 6 methyl protons in the isopropyl group of ibuprofen is selected, integrated, and the corresponding concentration of ibuprofen of 14.33 millimoles per litre is calculated using DSS as the reference. The implemented quantification procedure automatically takes into account any differences in signal acquisitions in the reference and test spectra. Scalar or J couplings, also called indirect dipole-dipole coupling, are mediated through chemical bonds connecting 2 spins. It is an indirect interaction between two nuclear spins, which arises from hyperfine interactions between the nuclei and local electrons. J-coupling contains information about bond distance and angles. Most importantly, J-coupling provides information on the connectivity of molecules. The energy levels of a nucleus will be affected by the spin state of nuclei nearby. The two nuclei that show this are said to be coupled to each other. This manifests in particular in cases where we have through-bond connectivity. J-coupling constants depend on the dihedral angles defined by the interacting spins. For example, the three-bond J-coupling constants are largest when two coupled spins are in the trans conformation and smallest for the goat conformation. This dependence is commonly used in protein NMR analysis to obtain constraints on the structurally important dihedral angles. However, for the small molecules free in solution, the fast rotation around unsaturated chemical bonds results in averaging of the observed J-coupling constants and obliteration of structural information encoded in the values of the constants. In ibuprofen free in solution, the fast rotation around indicated chemical bonds averages observed J-coupling constants. With understanding of the splitting patterns of resonance peaks caused by J-coupling, we can complete the assignment of the spectrum of ibuprofen. As the first step in multiplet pattern identification, we have to mark the relevant peaks in the spectrum. The process is known as peak picking. This can be achieved in a semi-automatic manner using the command pp. The most important parameters to set up is the solvent type, for example DMSO, and expected maximum and minimum peak intensities. The resulting peaks are to be further refined by manual inspection, during which non-relevant picked peaks are discarded. In this case, the two doublets flanking the main doublet are stemming from the methyl moieties containing 13C isotope of carbon, resulting in J-coupled splitting of 125 Hz. Carbon-13 is a natural stable isotope of carbon. It is one of the environmental isotopes, making up about 1.1% of all natural carbon on Earth. And missed peaks have to be added manually, shown in green. At the next step, picked peaks are semi-automatically grouped into the multiplets for further analysis. The strongest resonance, which was in the integration step, assigned to two methyl moieties in the isopropyl group, is identified as a doublet. The doublet splitting pattern appears if a spin or group of spins, as in this case, is J-coupled to a single spin 1/2. This spin, causing the doublet splitting of the protons from the two methyl groups, is indeed present in the structure and highlighted in green circle. Note that the protons from two adjacent methyl groups are not coupled to each other, since they are separated by 4 covalent bonds, resulting in J-coupling constants smaller than the resonance line width and thus not directly observed. Thus, the analysis of the multiplet pattern confirms the assignment made on the basis of the peak integration. The resonance of the single proton highlighted in magenta is split by J-coupling interactions to 3 protons in 1 methyl groups, shown in red, resulting in the quadruplet with the relative intensities of individual multiplet components 1, 3, 3, 1. The resonance of the single proton, highlighted in green, is split by multiple J-coupling interactions to 6 protons in 2 methyl groups, shown in red, and 2 protons in the methylene group, shown in blue, resulting in 6 + 2 + 1 = 9 individual multiplet components. Thus, the analysis of the multiplet patterns induced by the J-coupling interaction helped to resolve ambiguities in the assignment of 2 single proton groups, shown in green and magenta, when only integrals of the corresponding resonance peaks were used.